Hello, 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 and welcome back to another episode of Kerbal Space Programming. Kevin here, and well, I have been working pretty much all through the entire weekend trying to get our transfer maneuver script to a point where it maneuvers and transfers and all of that lovely stuff. Now, in the last episode, I made a quick follow-up episode pointing out one of the areas in which our initial attempt kind of fell on its face, but shortly after that, or I should say the next day after that, my good friend Alex Bragdon shared this on Twitter, that basically, if you leave the script running overnight, it will indeed find a great transfer to min-miss. So that was heartening, and of course that is to be expected, because the way that we've set this up with the genetic algorithm is that we give the thing hints as to what is a slightly better, and eventually, with the genetic algorithm, it will try everything, given enough time. Now, of course, if you were to run it again, it could be that the next time it would take a week, or it could be that it would take an hour, or it could be that it would find it instantly. But that is the nature of genetic algorithms, is that given enough time, they will try every possible solution. They're just going to really, really favor trying better solutions, and that's where that fitness function comes in. But here is the thing about fitness functions. They are very, very difficult to get right. And to kind of walk through, I want to walk through why this has been such a difficult challenge in trying to figure out how to give it a very good fitness function to get ourselves a good transfer maneuver. Here we've got a basic Gaussian function. I may have said Gaussian in the past. It's Gaussian. I'm wrong. I apologize. But I've gone ahead and asked Wolfram Alpha to graph this so that we can visualize it. We can see, okay, so ideally this is centered around 0. The input here would be the x-axis, and then our score would be the y-axis. So we're trying to get a value of 0, and if we do, then you get a score of 1. And if you're not, then you get less of 1. Now, the wonderful thing about this function is that there is a limit here. So there is a lot of favoritism. If we randomly happen to try a solution around here, it's going to favor it. But what happens if we're down in these, down in the dumps? Then it looks to the naive eye like there's not much of an indicator that, hey, we should really shift over that way. But let's go ahead and actually graph this from 5 to 10. So I'm just going to change the x-axis that we're looking at. Okay. From 0 to 2. There we go. Okay. So there we go. We've got that. It goes down to 2. So we're just looking at half of it now. Let's go ahead and just increment it one more time. There you go. Okay, so now we see what this curve looks like. And the interesting thing here is that we're seeing pretty much this exact same favoritism toward the 0 side. And that basically, no matter how much I advance this, and Wolfram Alpha seems to be being a little bit slow, you're going to see pretty much that exact same shape. So if everybody is doing very, very poorly, you're still going to see that same distribution where being slightly to the left, or being slightly in the correct direction, is going to be a big advantage in comparison with the other candidates as part of this genetic algorithm. So you see here, yeah, we've got pretty much the exact same shape. That something with a score of 4, even though that's terrible, we're looking at very, very tiny y coordinates, it's still orders of magnitude better than something that's 5 or 5.5. The big challenge, however, is if we look at, I'm going to go ahead and kind of mess this graph up. So I'm going to go back to the -2 to 2, but I'm going to put a maximum value on here. So I'm going to set it to maximum of 0.1. And you see what this is doing now is it's saying that by this point, as long, once we hit this range, now there's going to be no indication as to what is a better candidate. So if you end up somewhere out here, if you get a score of 5, you're going to get that y value of 0.1. If you have a score of 4, you're going to have that y value of 0.1. That means that when we try and pick the next generation of candidates, well, there's no reason to prefer a value of 5 or a value of 4. All we know is that once we're very close, then we can center in on the right value, but there's no way of helping the algorithm out in terms of figuring out these things when they're very far away from good solutions. So that's just for one input, though. Let's go ahead and change this to graph something in 3 dimensions. So I'm going to go ahead and say, let's see, e to the negative x squared plus e to the negative y squared. What if we're actually trying to optimize for 2 inputs? And you see here, it's gone ahead and brought up this lovely little 3D plot, and we can see now we can sort of visualize what we're doing. We say, okay, we've got some inputs. We've got X and we've got Y, and we're trying to give it some sort of fitness. F can stand for both function and fitness. We're saying that basically the height of this is the score that we want to give a particular solution. So we're feeding in these inputs and we say, if you got a value of 0, you got a value of 0. If they're both zeros, then that's great. This is the way that this is just a very, very simple function. So we've set it up so that zeros are the best values, and there are peaks here. Having one of them that's at 0, even if the other one is not, is still better than them both not being at 0. And so this is another example where you could basically climb your way up to the top here. And this is one that actually is pretty decent, although there is, of course, a bit of a problem. Let's imagine that the x value is our delta v score. Now, ideally, the perfect amount of delta v that it would take for us to transfer would be no delta v, so the value would be 0. But we're never going to get there. So now we've got an issue of how exactly does it balance out these two things? Because being here at this particular point on this axis is just as good, is just as fit a solution as being over here. And so now the algorithm does have the ability to say, I'm going to trade off not making the transfer in order to say some delta v, because the score is equivalent. And so we end up having to try and bias one of these in favor of optimizing, getting to the actual target at the expense of delta v. But then that means that the system ends up trying all of these really, really expensive delta v solutions, which is kind of where the nightmare exists. So let's do just one more. I'm just going to throw that max value back on here that we had from the first example. And here you see it's just as much of a mess here. Now, even unless we're very, very close in here, that there's no reason to move along this axis. Outside of this boundary. If this were to extend out, you'd see the same sort of, folded over piece of paper. I don't know. Yeah, saddle, I guess. Yeah, saddle. So it would still try and find the good y value, but it would never try and find the right x value unless it happened to stumble upon something inside here randomly. And depending on randomness for us to find a good solution is not a great idea. Now, I want to reiterate that we're not talking about the actual inputs to the maneuver node. We're not talking about the time and the delta v and all of that. We're actually, or the time and the delta v in the 3 directions. We're looking at the output, the different things that we're trying to score the resulting transfer orbit on. So whether or not it makes it out to minimus, what the periapsis is, what its inclination is, how much fuel it took to get there. Those are all different inputs. So in fact, we're dealing with something that is in 5-dimensional space, because you've got the 4 inputs plus that output, that height of this graph. I can't visualize 5 dimensions, and it gets very, very difficult because we're going to run into these exact same problems, only magnified into the crazy universe of 5 dimensions. So I spent a long time trying to clean up this transfer library, pulling out a bunch of these random numbers and making sure that they were constants, cleaning things up into smaller functions. I'm not going to go over this, though. If you're interested, you can go ahead and take a look on the GitHub, which is linked in the description. We've still got this, this terminate stuff, this create the fitness function. Here's the stuff that we want to talk about is the updated fitness score. So I've gone ahead and said, okay, we're going to split out the score and the penalties. So the score is we want something that has very little delta V. The penalties are, did it not do the things that it was supposed to do? We're going to split those out. I've got, and these are all in kind of their own little functions. We're taking the score and we're saying you're going to be the numerator and the penalties are going to be the denominator, though we make sure that we're not dividing by 0. Let's go ahead and look at the score function really quickly. And we see that all of this is a Gaussian function that's looking at the current maneuver and saying, what is your delta V? Is it 0? If so, high 5. And then this value here, remember, is just to give some extra width to the function so that you're not dealing with that same shape issue. So, okay, there we go. That's the only way that you can have a high score is having good delta V. But then there are the penalties, and those are pretty important. So the penalties here are if you have a bad inclination, if you have a bad periapsis, or if you have a bad transfer penalty. So let's look at what those are. The inclination penalty, I'm going to say if you didn't transfer to the target body at all, then you have a full penalty. Bad job. Otherwise, then let's go ahead and take a look at what your inclination is, what the inclination of your orbit is. So you got a good transfer, great. What is the inclination? If it is 0, high five, good job. Otherwise, we're going to go ahead and scale it down. So this is going to account for that whole retrograde orbit thing that we saw in the last video. We've got a periapsis thing that's doing the same thing. We're saying if you didn't transfer at all, you get full penalties. Otherwise, we're going to just go ahead and compare the periapsis that you have with the periapsis that we want and return a value that way. And then the sphere of influence transfer penalty. And this one is really more of kind of a hinter penalty, because we're trying to just hint like, there, go over to Minmus. And this is, if you did transfer, then we don't even need a penalty, right? No, you get no penalty from us because you already got there. Great. Otherwise, we're going to set the approach to the closest approach, which we're computing down below. We're saying, all right, based on the time of the maneuver and the time and an orbit after the time of the maneuver, saying what is the closest that you get to min-miss, and then we're going to return 1 minus that approach distance. If this approach distance is 0, then great. That's very, very good. Otherwise, not so great. If you're very far away from min-miss, if you didn't get anywhere near it, then you're going to have a high penalty score. So this closest approach is a little bit tricky. This is basically just doing some comparisons of our projected position based on the orbit, and it's kind of splitting the orbit by halves and trying to find the point where we stop approaching and we start moving away and saying, well, there's your closest approach time, and then it returns the separation at that time. So I'm not going to go into that because it's a little mathy and unwieldy. We're basically just pulling some slope values by comparing the position. This separation at function pulls in the position of our ship at a particular time and the position of the target at a particular time. This is something that you get from KOS. It presumes that you execute your maneuver nodes, and then it will say, here's roughly where you're going to be at a particular time. So that's very, very useful, and that gives us our closest approach. And this ends up being a very long file, lots of stuff. We also stopped using floating point values. We just said, all right, we're going to use regular binary, so 0, 1, 1 is 3. Or if we're trying to encode something that can be positive or negative, you have 0, 0, 1, or 1, 1 is 3, or 1, 0, 1, 1 is negative 3. So we're basically just using this first bit to be, are you positive or negative? And then what we end up doing is we actually take that and we divide it by the maximum value that could be in a 3-bit string. And so this ends up being, let's see, 3 over 5? Yeah, 3/5. And this would end up also being 3/5, and this would end up being negative 3/5. And that's how we can go ahead and store these fractions. So this just kind of handles all of that. And we've got that Gaussian function. Let's go ahead and see this in action. And alrighty, we are off. You can see that basically very little has ended up changing. We're still in the same position. I've got some, it's now debugging to here rather than displaying stuff on screen. I apologize for that because I know this is very, very small on your screen. But the gist of this is that, yes, it is still going to take a very long time. Obviously, it's entirely possible that during this run, we could discover a really, really great maneuver very, very fast and center on it. Theoretically, all of the function components are correct and valid. We're just not. It's just going to take a long time because we're searching, theoretically every possible direction. So 360 degrees times 360 to 180. I don't know. A lot of degrees, all of the degrees of a sphere, and and at all sorts of different amounts of delta V in those directions, which is going to take a long time to search down. The fitness function basically provides hints as to what are the good directions. You see, I guess it's at least flying off in the min-miss-esque direction. I've also shrunk down the number of candidates to 20 rather than 50 so that we can get kind of faster merging. Okay, so now it's getting. Oh, was that a flyby? I think I saw a flyby. That's at least something. But the point is that this could take a long time. It could take a short time. There's no way for us to know. And trying to run a mission around an unknown is particularly challenging. That it could, because of the degree of randomness, this could take a ridiculously long amount of time, longer than the heat death of the universe, and we just don't have that kind of time for this series. So Now it is time for us to take a look at a much more simple way of trying to get ourselves a decent orbit, and that is hill climbing. Now, the idea with hill climbing is it's another theoretically sort of AI, sort of machine learning, a little bit. The idea is that you take a starting value. If you imagine that same graph that we were looking at, you're looking at that map with elevations. You say, all right, here's a value. And you say, what happens if we move in any of these directions? Or do we get a better score if we move in any of those directions? If so, great. Let's go ahead and move in that direction. And that is all that it does until it can't find a better direction. And then it says, I'm king of the hill. I win. We're done. Now, there are some reasons to avoid this, and we talked about that in the last episode, in that we run the risk of finding what's called local optima, which are you found the top of a little hill when the mountain is somewhere else. But there are some ways that we can probably get around that. If we discover that we don't end up getting a transfer because we found something that looks like it'll get us close, but we can't get any closer, well, that's fine. We can just go ahead and restart with some different initial conditions. So let's go ahead and look at the code for actually trying something like that. So here's our hill climb algorithm, and this is really, really simple. You're going to enjoy this. So here's our seek. We're going to take some data. We're going to take a fitness function, and we're going to get a step size. So how much in any direction should we try and move? I'm going to say the next option is whatever our best neighbor is. And until the fitness function of the best neighbor is less than our current fitness, so until the only way that we can go is down, go ahead and set our data to the next data and set the next data to the best neighbor of that. So that's all that is. And we've got the details here of actually figuring out how you got this. Oh, I still have some extra printout here. We've got the details. So the best neighbor, we take in this, we say, okay, the best fitness is negative infinity. And the best one is 0. This is just setting up the variable. We say, okay, so for every neighbor in all of the possible neighbors that you've got, your fitness is the fitness function applied to that value. We say, if your fitness is better than the best one, then great, you're the best. And then we go ahead and loop. And so by the time we've looked at all of the neighbors, we say, all right, here's the best one. We're just going to return that just based on what the fitness function returned. So all we're doing really is we're sorting these values, not particularly efficiently, but we're sorting them. And for the neighbors, all we're going to do is we're going to say, okay, so you've got data. Data is going to be some sort of list. We'll say, all right, so for every value in that list, so maybe you passed in a list of 1, 2, 3 or whatever, we're going to say, okay, for each of those, we're going to create a neighbor that increments and a neighbor that decrements based on that step size. So if you passed in, 1, 2, then the neighbors are going to be 2, 2 and 0, 2 and 1, 1 and 1, 3. Of course, if you pass in a list of just 1, then your neighbors are going to be 2 and 0. And that is all that we're doing here. And in fact, all that so we're in fact passing in 4 different values because we're passing in the time to start the maneuver, we're passing in the delta V for the 3 directions that we can. So we're going to end up with far more neighbors than that. But that is all that there is to this file. Let's look at the actual updated transfer script that uses this. So here we've got this. We've got seek. We're saying, all right, same arguments. Take a target body and target periapsis. Remove any nodes. I've gone ahead and just pulled that out. We're going to say, okay, the data is some starting data. And we're going to say, set the data to hill climb, seek a data where the transfer fit function optimizes. And go ahead and step by 10. So go up by 10 seconds or down by 10 seconds and add 10 meters per second to delta V and just try that because we don't want to be around all day. We don't want to do this by ones. Go ahead and do that. Now, I haven't actually gotten to any of these, but what we can do here, the really cool thing is we can say, all right, we're just going to take whatever the maneuver is that we start with and make it a little bit better. And we don't have to try and come up with a fitness function that tries to encapsulate the value of all of these different attributes of whether the inclination's right and the periapsis is right. We're going to say, okay, first let's just get something that gets to min-miss. Then we'll worry about finding something that improves the inclination. Then we'll worry about something that fixes the periapsis. And then we'll worry about something that fixes the delta V. And of course, inside here, we'll probably say, as you're trying to fix the periapsis, if you end up, leaving min-miss, that's not good. So we'll go ahead and make sure that we don't do that. But we can go ahead and just gradually improve this thing without having to worry about encapsulating the logic for how do we value all of these things together. So the really fun thing is this starting data that we're going to try out, it's going to be basically a null maneuver. It's going to say, here's the starting time, but we're not using any delta V in any direction. We don't have to randomly generate a bunch of them. We don't have to worry about crossover. We're just going to say, here's a starting one. See if moving in any direction helps. And there we go. And we'll say, okay, then make a node from that data and go ahead and return that. So the transfer fitness takes in the target body and it's going to say, okay, so here's your score. The same thing. We're just going to say, if you transfer, then great, your score is 1. Otherwise, your score is negative. Here's another thing. We don't have to worry about the comparison between these values. We don't need to try and make sure that a twice better score is twice as good. We just need to make sure that it is better. Right? So we can actually just say, here's a negative value. We don't need to worry about these distributions anymore. We can say, all right, so your fitness is just going to be the negative of your closest approach. So if your closest approach was 1,000,000 miles away, then your score is negative 1,000,000. If your closest approach was 10 away, then your score is negative 10. And that's better. So great. If you actually transferred, then your score is 1 and ain't nobody going to beat that. So that's great. And we've got that same logic. I just went ahead and pulled that from before. We're just grabbing the closest approach, using the same stuff, using the same, right, so the transfer to is extracted out as well. Yeah, and here we go. The starting data is just the current time plus the lead time, and let's try 0 in the prograde direction, 0 in the radial direction, 0 in the normal direction, and the make node is just going to go ahead and create a node based on that list of 4 values. And remove any node just removes anything that is on our list. So this is a much simpler system, right? We're doing almost nothing. We're just saying, try tweaking a value and seeing if it's a little bit better. And that's it. And we're not even saying if it matches all of these conditions. We're just going to fix them one at a time. So for now, let's go ahead and see how this works, whether it gets there using using just the transfer fitness function. Alrighty, and this one is off. Let's see what it's doing. It's lagging a little bit, but here we go. It's got, yeah. So we started at a null maneuver. There's the maneuver that it added, and basically it just said, all right, give it 10 minutes, and from the current time, and it's trying to push itself in that direction. And it looks like if it gets out there, yeah. So its apoapsis, that's not so great. That's going to put it, well behind Mimus by the time it gets up there. And of course, you can see these fitness scores. Maybe you can't. They're a little small. But yes, we've got very, very negative fitness scores, but they are very, very slowly improving because it is taking these orbits and it's saying, well, your closest approach is probably here. And you may think, well, it probably ought to adjust the time. It is looking at every single direction and saying, is a slight increase to normal better? Is a slight increase to radial better? All that's happening is it's saying that you can see it's wobbling back and forth a tiny little bit, but it's finding, oop, okay. Got a moon encounter. Let's see what it does. All right. And you see what it's actually doing? It is now starting to adjust its time. It has gotten out there, and now it actually makes more sense. It is a better improvement to adjust the time. And so it goes ahead and switches to that strategy. Before, it just getting a higher orbit was a better strategy, and so that was the step that it took. Because it's not going to go ahead and combine these. It's just going to say, what about going that way? Is that, and it figures out which of the options is best, and then it says, we're doing that. So there we go. Now, okay, look at that. We're getting really, really close. Come on. You could do it. Get us a transfer. You can do it. Oh, it's dancing around. It is overshooting a little bit, but we're also off axis, which is not. Come on. All right. Come on. You can do it. All right. Yeah, it's adding too much. Well, there we go. Okay, it found it. There we go. That is the best one that it found. Let's take a look at, all right, 908 meters per second to delta V. So this looks like, with reference to, wow, that is one crazy maneuver. Okay. Yeah. Okay. So that's, Okay, so yes, that would fly by, and then we should almost honestly just do that. But okay, so 900 meters per second, and that is something that then we could refine. We could go ahead. It's the inclination is I think that's a good inclination. I'm not sure, but we could go ahead and say, okay, from here, let's go ahead and refine the inclination, and then let's go ahead and refine the periapsis, and then we can go ahead and say, if there's any delta V to be saved, let's go ahead and do that. But this is one where instead of trying all of this randomness, it managed to find a very efficient option just by saying, this is a slightly better approach than what we currently are at. We're only looking at that one option. So I think this is what we're going to go with in future episodes. I'm really excited to go ahead and add the additional 3 steps and let it go ahead and try and improve against those. But we will have to see how that works out in the next episode. So I will hope to see you then. Cheers.